Hey everyone, this video going to be looking at this intermolecular force worksheet. So what I did over here, just went ahead and I wrote down the chemical formula for each of these compounds. I also wrote down the name of the atom that's involved down here as well. And then the first thing we like to do with intermolecular forces, you have to know, is the molecule polar or nonpolar. It's really important to know that because that's going to tell you the type of intermolecular force that's going to be there. And the way to do that is you look at the difference in electronegativity and you look for polar covalent bonds if they're possible. So that's what I did over here. So the first two here, got fluorine and iodine. They're the same two atoms. So obviously the electronegativity is the difference is going to be zero. There's perfect sharing because both of them have the same electronegativity. And as a result, we're going to have a non-polar covalent bond. Well, how about the type of intermolecular force that's going to be happening here? It's going to be London dispersion. So both of these have London dispersion. However, what's going to happen is the London dispersion in iodine is going to be a little bit stronger just because it has more electrons and there's more opportunity for that temporary charge distribution, like the uneven charge distribution. So it happens much more in iodine than it does in fluorine. So fluorine is a gas at room temperature. Iodine is a solid because of that. Okay, so then we said, all right, let's check out the next one. So then I had this. I had sodium bromide and hydrogen fluoride. Well, sodium bromide, look at the electronegativity difference, it's 2.1, which means that you're going to have an ionic bond and you're going to have this. You're going to have true ions. These are true ions. So it's not a partial charge, it's a real charge. And you're going to have this crystal lattice happening too. So this whole thing, remember, is the crystal lattice structure. So it's that network of positive and negative ions. And if you look at a repeating unit in here, I call it an FU. It's nothing bad. It's not a bad word. That's shortcut for formula unit. So in chemistry, it's okay to say FU as long as it's in the context of formula units. So here, I don't have molecules, remember. Ionic compounds only have ions. All right, then I have this. I have hydrogen fluoride. You look at the electronegativity difference, it's 1.8, but the bonds are polar covalent. So this electronegativity difference is really a guideline. Sometimes you might have a high difference, but still have a polar covalent bond, not ionic. So here, we've got very strong attraction of the bonding electrons to fluorine. So it'll be quite a large negative partial charge here. And on the hydrogen, it's going to be positive. And as a result, you're going to have these opposite dipoles really attracting each other. And what happens then is you've got quite a bit of attraction. So remember, this is an example of a dipole-dipole bond. But remember, it's also an extreme example. So it has hydrogen. So this is an example of hydrogen bonding. So dipole-dipole, but extreme dipole-dipole, so it's a hydrogen bond intermolecular force. All right, let's look at the other examples here. Then I have methane and propane. So methane and propane, remember, are both hydrocarbons. And if you look at the difference in electronegativity, they're both 0.4. Very small, because we only have carbon and hydrogen here. So very small difference in electronegativity. So in other words, we don't have any charges with these molecules. There's no charges, and the only thing that can happen is London dispersion. So London dispersion for both of these. Now, why is it London dispersion? Again, temporary uneven distribution of charges. Who's going to have more London dispersion? Propane. Remember, it has a lot more electrons. It's a larger molecule, so there's more opportunity for the unevenness, the uneven distribution of the electrons to occur. So it's much more likely. So it has a higher attraction between molecules. And again, we talked about that in a previous video. Okay, at the bottom of the page, we've got water and we've got ammonia. Let's see what's happening here. So we already kind of know what to expect. Water and ammonia are both associated with, have hydrogen associated with the nitrogen or oxygen. So they're going to have a high electronegativity difference. So water is 1.2, ammonia is 0.8. So you're going to have positive and negative ends. So you're going to have these partial charges. And these partial charges are going to be attracting the opposite charge. And because there's such a charge difference, you're going to have dipole-dipole, and the dipole-dipole attraction is strong because of the hydrogen that's there and the other highly electronegative element. So we're going to have hydrogen bonds associated with this as well. So just at the bottom, here we go. You're going to have some hydrogen bonds. So you should be able to explain what type of intermolecular force something has based on the type of bond that's occurring. And then that's going to tell you, is it a polar molecule or is it going to be a non-polar molecule? So basically you have that. You also have this worksheet as well. This one is another good review. It has some really good solid test type questions on here. So work on this and you can check your answers as well. So that's it for intermolecular forces.